Hi, let's look at lesson 3. Today we're going to solve polynomial equations. And some of the essential things that you need to know is that we need to write the equation in the form of the polynomial on the left side and set the equation equal to 0. And then we want to factor the polynomial, and then we'll use the zero product law to find the roots. Now, if you've forgotten the zero product law, that basically says if you have two factors multiplied together and the answer is equal to 0, then it's an if-then statement. If that's the truth, then either one of the factors is 0 or both of the factors are 0. So let's jump right into the rules. We need to know how to factor the sum and the differences of cubes. So let's say you have a number cubed added to a number cubed, or the difference between two numbers cubed. You can think of this process as a number times a number times a number, and a number times a number times a number. So we're thinking of those conditions. Then we're adding them or we're subtracting them. So I like to tell my students I need a small set of parentheses and a large set of parentheses, and we're going to use these numbers down here that we're multiplying. So first we're going to identify that we have an A and a B that we're adding together. But over here we've got to cancel out a middle term, and we've got to keep the last term cubed. When you multiply this number times that number, that has to be a cubed. So thinking along those lines, let's look at using these numbers up. So if we have A times A, that would be A squared. So we've used up those two numbers. And then we have A times B, but we've got to do the opposite operation. So we want to subtract A times B. And then we have B times B, that's B squared. So that's how I like to remember that formula. It seems pretty straightforward. Now we're going to do the same thing with the difference of two cubes. So it's going to be the same thing, only opposite. So if we have A times A times A minus B times B times B, we're going to identify our two players, that's A and B, and the operation is subtract. So in the large parentheses, we've got A times A, so that's A squared. And we've got A times B, but we want to do the opposite operation, that's plus AB. And then B times B, that's B squared. And I'll let you expand those on your own time to see that they do give that end result of A cubed plus B cubed or A cubed minus B cubed. So following that same kind of logic, in the first example, x cubed is x times x times x, and 8 is 2 times 2 times 2. And over here on the second example, x times x times x, and 3 times 3 times 3 would give us 27. So using the pattern above, we want to identify our players. They are x and 2 with the operation of addition. And then we're going to take 2 at a time. X times x, switch the sign here to cancel out the middle term. 2 times x, and then keep the last term always plus 2 times 2. And over here for the difference of two cubes, same thing. The players are x and negative 3, or x minus 3, and then taking two terms at a time, x squared, 3 times x, but we want to add it so it cancels the middle term, and 3 times 3, that would be 9. So that's a pattern you're going to need to know. We also need to remember how to factor out using the GCF. That's our greatest common factor. So looking at this example, we have 18 and 27 and 45, and you can see that each of those terms is evenly divisible by 9, and our lowest power on the variable x to the fourth, x cubed, and x squared, our lowest power is x squared. So we can take out an x squared, and we could take out a 9. So 9 is a factor of each term, and x squared is a factor of each term. So if you think about distributing 9x squared to each one of those terms, to give us an 18x to the fourth, we need 9 times 2 and another x squared. To produce 27x cubed, we need a negative 3 and one more x. And then to give us 45, we need a positive 5. So that is an example of factoring out the GCF. And quadratic trinomials, you're probably very practiced with that from Algebra 1. So here in this example, I'm going to try a little bit more complicated version. And I like to use the box method. So I could either say 6x times 1x, or I could try 3x times 2x. And the last term is 4. So to get a 4, if I put a 4 here and a 1 here, or if I wanted to try a 2 here and a 2 there, you would find out that none of those will work to give us the middle term of 5. And what I'm thinking about is 6 times 1 and 4 times x. Well, 6x and 4x can't be combined to give us negative 5. And if we tried that with 2 here and a 2 here, we're going to see the same thing. 12 and 2 will never give us negative 5 in the middle. So it's sort of like a guess and check approach, but with a little bit of organization. So jumping over to my next option, I could either do 3x and 2x, because down this way, this is 6x squared. And I could try 2 times 2 to get me the 4 on the end. Or we could try 4 times 1. So looking at the diagonals here, so let me just clean this up a little bit. If we look at the diagonals, 6x and 4x will not give us negative 5. So I know that's out, and I can't trade anything around to get that. But I could also try 3x and 2x. That's definitely 6x squared for the first term. And 1 times 4 is definitely 4 for the last term. But 12 times 2 is not negative 5. So that's the reason I threw this option away and went with this option. So 3 times 2 is 6x squared, and 4 times 1 is 4. And if we look at 3x and 8x, I could easily get 3x and 8x to add up to negative 5 if the 8 was negative and the 3 was positive. So how can we make that happen? I can make the 8 negative and the 3 positive if we made 4 times 2 on this diagonal a negative, and 3 times 1 on this diagonal a positive. So that gives me the clue to factoring in some organized method. I need 3x minus 4 and 2x plus 1. So I prefer that method. You might do what my students call the Stretch Armstrong method and say 6 times 4 is 24, and we're going to rewrite the middle term, thinking about factors of 24 that add up to be negative 5. So I immediately think of 8 and 3. If we had 3x minus 8x, that would give us the 6 times 4 for 24. And then the last term again would be minus 4. So then we would factor by grouping, and that grouping in the first two terms, thinking about the first two terms, we could take a 3x outside, and that would give us 2x plus 1. And then we've got to have the same 2x plus 1. So in the second two terms, we would take negative 4 outside, and you can see where the 3x minus 4 came from our box method, and then the 2x plus 1 came from our box method. So whichever method works for you, you pick one and experiment around, and pretty soon you'll be an expert. On the next page, we're looking at perfect square trinomials. In this pattern, you can tell that to get the a squared, you're going to distribute this binomial twice. So it's like factors of 64 are 8 times 8, and 8 plus 8 gives me 16. So I have a pair of factors, x plus 8 times x plus 8. And if you think about it, that binomial squared, if you think about it this way, I'm going to square the first term, that's x squared. I'm going to square the last term, that's 64 in my example over here. And then we're going to multiply the two together, a times b, which is 8 and x, and double that. 8x doubled is 16x. So you can really quickly check that by expanding using that little simple trick. And then x squared minus 16x plus 64, it's going to be the same thing, just subtraction. So our two factors are x minus 8 times x minus 8, because inside and outside gives us that negative 16. And the last two terms in the distributive property gives us that 64 positive on the end. So we have a pair of binomials. Those binomials squared produces this perfect square trinomial. So from our first lesson, naming conventions of polynomials, this is a perfect square trinomial, and it can be factored as the difference of these terms, and we have a binomial squared. So there's two linear factors, x minus 8, and combining them together, this is called a binomial squared. That product is a perfect square trinomial in either case. So this is a lot of review and factoring. Now the difference of two squares, that's when we have a squared minus b squared. The difference of two squares are conjugate terms, a plus b and a minus b. So the difference of two squares can be factored, but the sum of two squares is prime. That cannot be factored. So don't let this plus sign trick you. You can't put two pluses or two minuses. It just doesn't work. So when we think about factoring in Algebra 2, the sum of the difference of two squares, you can think of taking the square root of each of those terms. So this is my a term in our rule over here, and this is my b term in our rule. And if you take the square root of 4x squared, you're going to find that 2x is the a term. So we've got 2x in the first parentheses and 2x in the second parentheses, and we want the outside and inside terms to cancel, so we need one positive, one negative, and you know that the square root of 3 times the square root of 3 is the square root of 9, and the square root of 9 is positive 3. So we're good to go with factoring the difference of two squares in that way. Now factoring by grouping, we're going to do just like we did in the earlier example, and we're going to think about the first two terms and then the second two terms. So taking out the greatest common factor between x cubed and 4x squared would be an x squared, and that would leave an x minus 4. Now to make this method work, we need to have an x minus 4 in the second two terms. So looking over here at the negative 9 and the positive 36, we could take out a factor of negative 9. Then you can see where our two factors come from. One factor is x minus 4, and the other factor is the leftover terms, the GCFs, x squared minus 9. But when you think about x squared minus 9, you see it's also the difference of two squares, like the previous example. So we want to factor that as much as possible. Need to give myself a little writing room here. So factoring x squared minus 9 times x minus 4, we can rewrite that to be x plus 3 times x minus 3 times x minus 4. And that would be factoring that cubic polynomial in linear factors here, where if this was an equation, we could solve. And here comes our sum and differences of cubes again, just for your practice. We're going to identify, these are a little bit more difficult, so we can identify our A term is the cube root of 64x cubed, and our B term is the cube root of 1, because these are two perfect cubes. So our A term is 4x, and our B term is 1. And following our pattern with small parentheses and large parentheses, we need our players, 4x and positive 1. And then 4x times 4x is 16x squared. 4x times 1 is 4x, but we want to reverse, we want to do the inverse operation, that would be subtract. And then 1 times 1 is 1, so we're learning how to use that pattern. And then for the a cubed minus b cubed, we have the same thing, so we've got the two terms. 64x cubed is going to give us 4x times 4x times 4x, and we've got subtracting 1 times 1 times 1. Small parentheses, large parentheses. So our players are 4x minus 1, or 4x and negative 1, and then two terms at a time, 4x times 4x, 4x times negative 1, and do the inverse operation, so we add, and then 1 times 1, that's always positive on the last. So not so bad. Once you do about 1 million of them, and the pattern just kind of turns out to be obvious. Let's look here at solving by factoring. That's our next topic. So solving by factoring, our equation is already set equal to 0, and we want to think about when is x squared minus 1 0. So using the square root rule for solving, when x squared is equal to 1, and we take the square root of the left side, we've got to remember to take both positive and negative square roots, because we are the one introducing the square root operation. So x is either going to be positive 1 or negative 1. And when we look at imaginary solutions, on the second factor, x squared plus 4 is equal to 0. When we're talking about the complex number system, then we're allowed to take the square root of a negative number. So the square root of x squared is positive or negative square root of negative 4. And we know the square root of negative 1 is I. So the square root of 4 is 2. And my imaginary solutions are 2i and negative 2i. So we have 4 solutions, because using distributive property, x squared times x squared would be an x to the 4th equation, and that means we need to have 4 zeros. We have 2 real zeros, and we have 2 imaginary zeros or complex zeros. In part B, your job is going to be to rewrite in standard form. Moving everything to the left is x to the 5th minus 5x to the 4th plus 4x cubed and plus 2x cubed, and then our equation is equal to 0. Collecting like terms, we're going to have x to the 5th minus 5x to the 4th plus 6x cubed. The greatest common factor is x cubed. That leaves us a trinomial, a quadratic trinomial that has 2 linear factors. If we have factors of 6 that add to give us -5 in the middle, those factors would be x minus 3 and x minus 2. So we have 5 solutions. Since our degree is power 5, 3 of the solutions are 0, so that's an odd multiplicity, or multiplicity 3. And then we have a solution at x minus 3 equals 0, so 3 is a root or a solution. And then x minus 2 equals 0, which gives us 2 as a solution. So we have 3 solutions, 0, 3, and 2. 3 places where the graph is going to cross the x-axis on that polynomial function. Moving on to example 2, we want to find the real or the imaginary solutions for each polynomial. And in this case, x to the 4th equals 16. We're going to move the 16 over, and we're going to factor x squared plus 4. This is the difference of two squares, x squared minus 4. And I'm going to take the square root approach. So then I can find the real solutions and the imaginary solutions. If we had, just over here on the side, if we had taken the 4th root of x to the 4th and gotten 4, and considered both positive and negative 4th root of 16, we would have only gotten the 2 real solutions of 2. But to find the imaginary solutions, we have to use factoring in this approach to be able to do that. So x squared plus 4 equals 0 when x squared is -4, and it's similar to the previous lesson or example where x is going to be the positive or negative square root of -4, and our 2 imaginary solutions are positive 2i and negative 2i. And then these x squared equals positive 4 when x is positive or negative square root of 4. And there's my 2 real solutions. So power 4, we're looking for 4 solutions. We found all 4. In example B, again, moving everything to the left so we can set the equation equal to 0. Factor out the GCF. Consider the quadratic trinomial. Do we have factors of 8? That would make -8 when we multiplied, but they would add up to positive 2 when we added. Those factors would be positive 4 and -2. Our solutions are 0, -4, and positive 2. It's a cubic polynomial. We have 3 solutions. They're all real in that case. And then on part C, first we'll have to distribute and then collect like terms. But notice when we distribute on the right and the left, there's an 8x on the left, an 8x on the right. They're going to subtract to 0 when we collect like terms on one side. And this one's a little tricky. So we have the difference of two cubes. Small parentheses, large parentheses. X minus 2 are my A and B terms. X times X, opposite operation, 2 times X plus 2 times 2. So this piece is very simple. We know that X minus 2 is 0 when X is 2. But this part, we're going to need to use the quadratic formula in this case. So quadratic formula. You remember that. X is the opposite of B, plus or minus the square root of B squared minus 4 times A, which is 1, times C, which is 4, all divided by 2 times A, and 2 times 1 is 2. So underneath our vinculum here, this grouping symbol is called a vinculum, we got 4 minus 16. So that looks like the square root of 4 minus 16, negative 12. So I want to think about negative 12 as a negative 4 times a 3 underneath that square root symbol. And when you think about the square root of negative 4, this is 2i, right? So we already know that's 2i. So 2i. And the square root of 3 stays behind. And then you have a dilemma here. If you can divide this 2 into both terms in the numerator, 2 goes into negative 2, negative 1 time, and 2 goes into positive 2, positive 1 time, then you can divide across that fraction bar. But it's got to go into both factors, this one and this one evenly. Otherwise, you can't do that. So then we have our two imaginary answers, negative 1 plus I square roots of 3, and negative 1 minus I square roots of 3. I'm going to write them together. This was a cubic polynomial. We had one real solution and two imaginary solutions. Now, this lesson is really long, so this would be a good place to stop and come back and finish the lesson at another time. I'm going to continue my video. We're going to look at solving this polynomial using two different methods, either the intersect feature on your calculator or the zero feature on your calculator. To use the intersect feature, you notice that I graphed the left part of the equation, that's this red cubic, and then I graphed the y part of the equation, that's the blue linear equation. So I graphed the left side and the right side, and where they're equal means that point of intersection. Using the calculator, I'm going to find out that this point of intersection intersects at negative 1.839 and negative 2.839. So the solution is the x value. That means my x answer is about negative 1.839. In the second method, we want to rewrite the equation, which means we would end up graphing this graph. The green graph would be x cubed plus x squared minus x plus 1. And then I would use the zero feature, and the zero of the polynomial needs to be the same answer. Negative 1.839 is my zero. So whichever method you prefer, either one works, and they're both valid. Now in example 4, we got two more examples. These are practical or word problems. So let's find three consecutive integers whose product is 480 more than the sum. So you got a lot of vocabulary terms here. I'm going to use x as my integer. That's my first integer. Now, when we have three consecutive integers, an integer means I'm just adding 1 to the previous number. So my second integer would be x plus 1, and my third integer would be x plus 2. So this is the second integer, and the x plus 2 would be my third integer. So we're going to put the sentence together in an equation form. The three consecutive integers, when I add them up, x plus 1 plus x plus 2, and I have 480 more than the product. Well, what does the product mean? That's to multiply. So x times x plus 1 times x plus 2. So over here on the left, it looks like I have 1, 2, 3 x's and 3 more and 480. So on the left, I have 3x plus 483. But on the right, I have x times the product of these two. So those is x squared plus 3x plus 2. So the right side of the equation is x cubed plus 3x squared plus 2x. So now we want to collect everything on one side of the equation. So I'm going to put everything on the left. That's going to be x cubed plus 3x squared plus 2x. And then if I subtract 3x from this, subtracting 3x, and subtract 483 to keep it all on one side, everything is collected on one side of the equation. And what do we got? Collecting like terms, that looks like x cubed plus 3x squared minus x minus 483. Now, I don't have room to show you what I did on my graph, but I went to my graphing calculator and used the 0 feature. And using that 0 feature, I found out by the graph that 7 was the 0. So if we have, back to the beginning here, if we have x as my integer 7, then x plus 1 is 8, and x plus 2 would be 9. So my answers would be 8 and 9. So let's make a note of that. Our answers are 7, 8, and 9. Then the very last example, we have the Perez twins. They were born 2 years after their oldest sister. And this year, the product of the three siblings' ages is exactly 4,558 more than the sum of their ages. How old are the twins? Well, putting that together, let's say x is going to be the number to represent the twins' age, because that's what we want to find, is how old are the twins. And they were born 2 years after their oldest sister. So x plus 2 years is the older sister's age. So we have two variables to work with. And it says that the product of the three siblings' ages, so if I multiply x times x times x plus 2, that's the three children. Their age is exactly 4,558 more, so that means to add the sum of their ages. So we're going to add up their ages. Twin 1, twin 2, the older sister. When I add up their ages and I add 4,558 more, that's the same as the product of their ages, because here's the equal sign. So we have x times x times x, that's x cubed, and x times 2, That's 2x squared. And adding up x and x and x and 2 and 4558 looks like 3x plus 4560. Collecting like terms and setting the equation equal to 0. I'm going to use my calculator to get a graph of that. I've got plenty of room here on my paper. So by graphing, I can see you got to set your window really big so that you can see the graph here. And my graph looks something like that. And I'm coming over here to look at this because this is going to be the age of the twins right here. So the twins' age looks like it's crossing the x-axis at 16. So using the graphing method, I know that the twins are 16 years old. And this is a long lesson. Hopefully you can break it up into 2 days so you don't have to watch 35 minutes of video. But this was lesson 3 in Unit 5.